For this year's Human-Powered Vehicle Challenge, an annual competition put on by the American Society of Mechanical Engineers, ASME, senior design students from the University of Rochester have designed the vehicle Venandi, or Hunter in Latin. While this vehicle could not be fabricated due to changes caused by COVID-19, the team has formulated a complete design, done analysis, and created plans for theoretical manufacturing. During this presentation, we will cover the background research done for this project, the specifications and requirements chosen, how different concepts were selected, the analysis performed on the various systems, manufacturing plans, the sponsorship received for the project and the cost analysis for parts and manufacturing, and finally a conclusion on the work done and acknowledgements. These three views of the vehicle were created in Siemens NX. The vehicle features a two-wheel, front-wheel drive recumbent design with an adjustable seat to be able to fit each team member. The main frame of the vehicle is a backbone structure made of foam layered in carbon fiber with crush tubes sticking out of the carbon fiber to connect to the rollover protection system. The rollover protection system includes the hoop above the rider's head and the two additional support bars connected from the top hoop to the carbon fiber frame below, which extend wider than the rider's shoulders. The past 2 years, senior design groups in the U of R Mechanical Engineering Department have participated in the HPVC. The previous designs produced were similar in overall concept, as they were both three-wheel recumbent tadpole-style vehicles. This year's team decided to take a new approach and look at the option of building a two-wheel recumbent vehicle. Additionally, research was done on this style of vehicle competed in the previous HPV competitions, such as the vehicle built by La Universidad de los Andes in 2017. The team also found a commercial riding bike in this style, the cruise bike. These both helped to highlight the advantages of this style of vehicle, such as the simplicity in the frame, the ability to make the vehicle very light, and the ability to simplify the drivetrain system. Requirements and specifications were outlined by the team prior to concept generation in order to have a frame of reference for the design. Some of these were provided by the ASME 2020 HPVC rulebook, such as coming to a complete stop from 25 kilometers per hour in 6 meters and being able to do a 8-meter radius turn. Others were decided on by the team, such as being able to adjust the seating for people between the heights of 5'2" and 6'9", and incorporating carbon fiber in the frame, both to help performance and as challenges that have not been done by U of R teams in the past. In order to do concept selection for drivetrain, steering, and brakes, 2 Pew matrices were set up to decide between 2- and 3-wheel drive and to decide on front-wheel versus rear-wheel drive. As dictated in the table, it was deemed best to create a 2-wheel, front-wheel drive vehicle.
For the finite element analysis of the frame, we tested 4 static load cases and 1 eigenvalue analysis. All the load cases used the same base mesh, with 1D elements making up the steel tube section of the frame, 2D elements making up the carbon fiber composite skin of the frame, and 3D elements making up the final foam core of the frame. The first of the 4 load cases is a 3 times gravity bump load. This is to simulate the vehicle going over a harsh bump and being quickly accelerated. A 245-pound concentrated mass is located at the approximate center of mass of the driver and connected to the points and faces that the seat is connected to. The frame is constrained at the rear wheel and at the front wheel, and also at the top of the roll bar to constrain the rotation. The second load case is to simulate the clamping force that the frame experiences due to the seat and the rider. The loads were calculated by the seat sub-team, assuming that the rider is 245 pounds. The same constraints are on this load case as on load case 1. The third load case is the side roll protection system test, described in the ASME HPVC rulebook, having a 1,330 Newton force in the positive X at shoulder height. It is constrained at the connection points of the seat belts as per the ASME regulations. The fourth load case is the top roll protection system test, again from the HPVC rulebook. This has a 2,670 Newton force on the top roll bar, 12 degrees from vertical, and is again constrained on the seatbelt connection points. Shown are the results for all 4 load cases. Also shown is the yield stress of each material and the calculated factor of safety. Highlighted are the maximum values for each material, showing that each of the load cases, aside from the side RPS test, results in a maximum stress case. Load case 1, the bump load, has a maximum stress in the carbon fiber. Load case 2 has a maximum stress in the vinyl foam. Load case 4 results in a maximum stress in the steel tubing and a maximum deflection. The factor of safety target was 1.9, higher than previous years of the U of R HPVC entry, as this year the team is using materials that the team and advisors have little experience with, such as the carbon fiber. Shown here are the critical results for the carbon fiber in load case 1 and the critical results for vinyl foam in load case 2. Shown here are the critical results for the steel tube in load case 4 and the critical results for displacement in load case 4. These are the results for the eigenvalue analysis. This shows the frequency that the vehicle will tend to resonate at, and shown on the table are some frequencies that the vehicle is likely to experience excitation at. For pedaling, it is expected that the vehicle will be excited at twice the frequency of the pedaling, which is why 60 RPM corresponds to 2 Hz. The frequency due to motion was calculated using the wheel diameter and the velocity of the wheel. The eigenvalue analysis was performed on the mesh from load case 1, including the 245-pound mass. The lowest resulting frequency was 6.77 Hz, showing that the vehicle would tend to resonate at a frequency higher than the expected excitation.
And I'm now going to talk about the seat design. So this is a foldable seat purchased from a recumbent bike company. And in order to fit this seat to our frame, we need to custom make a C-shaped mounting bracket shown in the picture above. And it's going to be made from an 8-gauge aluminum sheet with some holes on it. And the mounting of the seat will be purely based on gravity and friction. The tightened two M4 bolts go through the bracket, plus the rubber pads stick to the inside of the bracket are able to provide sufficient friction to counter the force pushed by the driver when riding. This design not only reduces the weight by eliminating the need for heavy metal rail, but also makes adjusting seat very easy. You can just loose the bolts and the seat can be moved along the frame freely and tighten it to hold it in place.
In the original design of the vehicle, the front triangle was connected to the frame directly. A hole was to be created through the frame into which the head tube would fit. However, due to the nature of carbon fiber manufacturing, this process would need to be extremely precise. If the hole was created at the wrong angle, the front triangle may not fit. In order to avoid this problem, a connection block was designed. The idea was to clamp the head tube of the vehicle in such a way that the angle could be adjusted to account for the actual manufactured frame. The block consists of 4 pieces, all made of aluminum, a main body that connects to the frame through bolts, 2 clamping pieces designed to hold the head tube in place, and the head tube itself. Analysis was performed on the system to ensure that it would not fail. Specifically, a model was created with forces to represent real riding conditions. There is a 35-pound force directed toward the rider from the handlebars. There's a 200-pound force directed away from the front triangle to account for the pedal force, and there is an 85-pound force upward to model the wheel surface contact. The rest of the frame is modeled as a full constraint through the bolt holes in the main body. The results from the analysis of the connection block can be seen here. The maximum stress occurs in the head tube, which is a block part, and is therefore known not to fail in these conditions. The highest stress in the other components occurs at the fixed constraint with a value of 10,472.5 psi. This is well below the yield strength of 6061 aluminum. A convergence study was performed, and it was found that between a mesh size of 0.2 inches and 0.1 inches, the max stress result changed by only 1.7%, well within an acceptable range for this design. Finally, a fundamental statics analysis found that the axial stress in the bolts was approximately 9,000 psi, also well below the rated strength from McMaster Carr. Therefore, the front triangle connection block was deemed to be safe.
After a brief research on different landing gears, it was learned that buying a kickstand would save both cost and time. Therefore, the team investigated 2 different kickstands, a rear axle kickstand and a lumen trail kickstand, as shown in figure 1 and 2 respectively. Both have double leg and provide enough clearance for a 26-inch rear tire. Even though lumen trail double leg kickstand is adjustable, it would have to be incorporated into the carbon fiber frame, and that would create unnecessary complications. Hence, the rear axle double leg kickstand was chosen for our design. Two different analyses were performed on the rear axle kickstand to make sure it fits the design criteria. First was a finite element analysis to see if it would handle the bike load of around 40 pounds. As we can see from figure 1 and table 1, stress form are much lower than the tensile strength of steel. Therefore, the landing gear chosen can support the bike. Second analysis was on the stability of the bike when the landing gear is used. As we can see from figure 3, the center of gravity falls within the triangle formed between 3 points of ground contact, that is, the 2 from the landing gear and 1 from the front tire, which proves that the bike should remain stable under the force of gravity. Fairing is a useful design resource for reducing drag without increasing the weight of the bike significantly. Last year's team used a fairing, but because it was mounted in only 2 points, it was not fully stable and had harmonic excitation. So this year's two-wheel design approach inherently generates a narrower frame, further forcing the importance of a stable mounting of the fairing. The team considered fairing designs that could have at least 4 connection points to the frame. The fairing sub-team analyzed 3 different fairing options: a full front windshield as shown in figure 1 and a half front windshield as shown in figure 2, and the third was a no fairing option. The aerodynamic analysis was done using NX Advanced Flow Solver. A fluid domain was created around the bike with a relative mesh size of 0.01 inch. Two boundary conditions were set: an inlet on the front and an opening in the back. The inlet velocity was changed from 5 miles per hour to 20 miles per hour. Figure 3 and Figure 4 show the velocity profile on our two fairing designs. The net drag force for a wind speed of 10 miles per hour is tabulated in table 1, which shows that the model with no fairing experiences the least drag. Furthermore, a velocity versus drag analysis was done to see if a fairing would perform better under different velocities, but the results were still negative. Therefore, the team decided not to have a fairing.
The components listed to the right were chosen by the team and belong to the SRAM Rifle 1 componentry set. The set was donated by the SRAM company. The time and tools needed to complete the manufacturing plan is listed on the table. Specialty tools such as Park 2 BBT79 can be borrowed from local bicycle shops, and the other common tools can be borrowed from UR machine shops. The total drivetrain assembly process can be completed in 1 day.
Once again, utilizing common bicycle components, the front triangle will be mounted through the attachment mentioned in previous slides. The steering axis will be supported by a headset unit, which is comprised of 2 bearings at both ends of the head tube, labeled Part C. These bearings are specifically designed to support extreme loads encountered when riding a bicycle and will ensure smooth turning of the vehicle even on rough road conditions. This manufacturing process will consist of press-fitting the bearing sets into the head tube, then removing the handlebar boom and slotting the front triangle in place. A stem screw will be used to secure the bearing set against the fork races, eliminating any play within the system. The head tube shown in Part C and to the figure on the right, the headset bearing set, will be purchased from a third-party seller. The blocks at B and D, supporting and side blocks, will be milled from 6061 aluminum.
The manufacturing of the frame starts with the foam core of the unibody carbon fiber frame. A CNC machine would cut 1-inch thick foam pieces that get glued together with resin, creating the shape seen here. After this, carbon fiber sheets would get fitted over the core, and resin would be pumped into the sheets to get them to set and become hard. This is repeated until 4 layers of carbon fiber are over the foam core. After the frame is constructed, connection plates for the back wheel would be plasma cut from 1/8 inch thick steel and be connected to the rear. The rollover protection system for both the side and the top would be created from 1/2 inch, 1 1/4 inch, and 1 1/2 inch thick steel pipes that would be notched and cut at specific angles and then MIG welded together. This RPS system would be attached to the front of the frame through a crush tube that would help alleviate high stresses on the carbon fiber frame. Connection plates for both the front and rear connection points of the RPS would also be plasma cut and inlaid into the foam core prior to the carbon fiber pour.
One goal of this year's HPV team was to spend less than had been spent in the past by recycling parts and using donated or used parts to be more environmentally conscious. A cost analysis was done on parts and manufacturing for each subsection of the vehicle. Additionally, costs for travel, room and board, and the competition fees were added to the build cost, and the total overall cost came to $4,696.44. This project is funded by the U of R Mechanical Engineering Department, who contributed the original $2,000 to this project. Through fundraising, $1,900 was raised, as well as $1,400 in parts. Additionally, the team had planned a fundraiser that was predicted to raise $500 at least. All in all, the team raised $5,800, allowing for wiggle room in the budget to cover unexpected changes. While the team is disappointed that we were never able to build our human-powered vehicle and compete it, we are glad that we were able to do the research and create this design. We hope that future U of R teams can use the ideas and work that this year did to help them formulate an idea for a human-powered vehicle. We would like to acknowledge our advisors, Dr. Christopher Muir and Dr. Laura Slane, as well as the University of Rochester Mechanical Engineering Department, the University of Rochester Office of Deans, the ASME Rochester Chapter, Cruise Bike Company, SRAM, and Rochester Community Bikes for their support, guidance, and sponsorship.